Hi everyone, so we are going to go over sections 5.4 and 5.5 today. 5.4 is on gas stoichiometry. So as you can see here is your STP equation for a gas. So this is for any gas at STP, standard temperature and pressure. 1 mole of gas will occupy 22.4 liters. So you learned that conversion in first year chemistry. This is a new equation right here. The MM stands for molar mass. The little d is density. R is the universal gas constant, temperature in Kelvin, and then of course pressure right here. Okay? Now the important thing to know about this equation is it has to be a gas and it has to be at STP. Okay, so let's underline the STP part. Oops, pen. All right, STP. And if it's not at STP, then you would have to use other information that is provided in the problem, and then most likely it will probably be some variation of this equation here. All right, so I'm going to go to a new page, and I want to show you how this equation is derived. Let's take a look at this equation, and I'm going to show you how it is derived from PV equals nRT. This equation right here is not on the pink sheet. So if you would like to use this equation, you would have to have it memorized. And if you don't have it memorized, it's okay too, because I'm going to show you how you can figure it out just by using PV equals nRT. Okay? All right, so then what we're going to do is for N, I'm going to substitute grams over molar mass for N. Okay, don't forget, N represents moles. Okay, so then to get moles, we would take the grams and divide it by the molar mass, right? And that will give us moles. Okay, so then let's make that substitution. So PV equals grams over molar mass times RT. Okay, and then what we're going to do here is we are going to multiply by M and M, molar mass, on both sides. And then, so let's just rewrite that part and see what that looks like. Okay, so if we end up multiplying by molar mass on both sides, so then it's going to look like this. Molar mass, PV equals grams RT, right? And then let's isolate the molar mass by itself. So then let's divide by P and V on both sides. So then divide by P and V on both sides. So that crosses out there. Therefore, molar mass equals GRT over PV. Okay? And then if you take a look here, grams over volume. So if you remember, grams over volume, that is density. Okay, remember, density is mass per volume. Okay, it's a mass and volume relationship. So that is how they get density. Okay, so that there equals, oops, pen, equals density. So then you can rewrite the equation, then it's molar mass equals density times RT over P. So that is how that equation is derived. Now if we go back to the help sheet, let's take a look at this problem right here. What volume will 1.18 moles of oxygen occupy at STP? So notice that it says STP, so that means we can use our conversion of 1 mole equals 22.4 liters. Oops. Okay. All right, so now let's do our math. Start off with the number that's given to you in the problem, 1.18 moles of O2. Okay, and then the mole's going to go on the bottom, so the units cancel, and then the 22.4 liters will go on top. Okay, so moles cross out, and then you're just going to multiply across here, 1.18 times 22.4 liters, and then I got 26.4 liters, but you should check my work. Okay, so 22.4 liters there. All right, let's take a look at the next problem. So we have 0.5 liters of hydrogen gas are reacted with 0.600 liters of oxygen. It's at STP. The question is, what volume will the water occupy at 1 atm and 350 degrees Celsius? Okay, so if you notice here, we're given 0.5 liters of hydrogen and 0.6 liters of the oxygen. So notice here we are given quantities for both reactants. So if we are given quantities of both reactants, then this is a limiting reagent problem. Okay, so we're going to do our two separate equations. So remember, stoichiometry from here to there, and then do another one from there to there. Okay, so let's go ahead and do that. And then let's take a look at what we have going on. So let's start off with the hydrogen, so 0.5 liters of hydrogen. Okay, so since this is at STP, then we can use 22.4 liters per 1 mole, and then we do the mole ratio. Okay, the one we're going to goes on top, so 2 moles of H2O for every 2 moles of hydrogen. Okay, and then you're going to do the same thing with the second equation, so then 0.6 liters of oxygen, 22.4 liters per 1 mole. And then when you're going to goes on top, so 2 moles of water for every 1 mole of O2. Now you're probably wondering why I only went to the moles of water for both of them and then I didn't convert it to liters there. Yes, we do eventually want to convert it to the liters or the volume of the water, but notice that the conditions change. Okay, we have 1 atm, which is standard pressure, but the temperature is not at STP. So then once we find out which one is limiting, okay, so we'll get the moles here, then we're going to have to use a different equation in order to solve for the volume, because we can't use 22.4 liters because that's at STP. Okay, and these conditions, once again, are not at STP because this is not standard temperature. All right, so let's put this into our calculator. You guys need to check my math to make sure I do it right. So 0.5 divide by 22.4, and then that's just 1. Okay, so this one I got 0.0223 moles. All right, let's check the other one. 0.6 divided by 22.4 times 2. That one I got 0.0536 moles. Okay, so then when you do the two separate equations, we have to find out which one is limiting, because remember, you can only make as much product as your limiting reagent. So this one here is the limiting one. Okay, so we're going to use that value. All right, so that means that the hydrogen was limiting. So we're going to, and that was, we went to water. Remember, we went to water there. So that's that will be the mole amount that we're going to use in the final equation. All right, so the final equation that we're going to use to convert to liters is going to be PV equals nRT. once again, we cannot use 22.4 liters because the conditions are no longer at STP. So we're going to use PV equals nRT, and then we're going to solve for volume. Okay, so let's plug in the numbers. Pressure is 1 atm. Volume is our X. N are the moles, 0.0223 moles. R is the universal gas constant. Let me slide this over. Okay, so then R is 0.0, I rounded it, 0.0821. Temperature, add 273 to that, so then it ends up being 623 Kelvin. Right? Okay, now solve for X. Okay, and then when you solve for X, once again, always double check my math, but then I get 1.14 liters. Okay, so you should double check that to make sure I did it correct. All right, let's take a look at the next problem. Let's see, what does that say? All right, a gas at 34 degrees Celsius. So we have temperature, 1.75 atm, so we have temperature. We have pressure. We have density. And it wants us to calculate the molar mass. That's what we're trying to find. Okay? So then therefore we can use the new density equation. So let's take a look at that. So molar mass equals dRT over P. We call this the dirt P equation. Okay, I call it the dirt P equation. All right, then we're going to plug in our numbers. Density is 3.40 grams per liter. R is the gas constant, 0.0821. And then temperature in Kelvin, so add 273 to that. So that's 307. And then pressure goes on the bottom. Pressure is 1.87. Oops, sorry, 75. Erase. Erase, erase. Okay, 1.75 ATM there. All right, so then we solve for the molar mass. Okay, plug all of that into your calculator. And then, if you do it correctly, and I'm going to round to 3 sig figs here, then you should get 49.0. And the units for molar mass, if you were to plug in, I didn't write them out here. Okay, I didn't write out all the units for R there. But if you write it all out and everything and put your Kelvin in there and your atmospheres here, you should see what gets crossed out and then what is left. Or you can also just remember what your units are for molar mass. So if you remember, your units for molar mass are grams per mole. Okay, so 49 grams per mole. This is the last thing that I want to go over for today. So this is Dalton's Law, partial pressures. So we did the whole POGL on partial pressures. So remember, according to Dalton's Law, if we have a mixture of gases, each gas will exert its own pressure. Okay, so then there's this new concept here called mole fraction. All right, mole fraction. This looks like, I know, yes, it looks like an X, but it's not an X. It is a Greek letter. It is the Greek letter chi. Okay, it is the Greek letter chi. What chi is telling us, or what this equation is representing, it's saying that chi, or the mole fraction, it's basically part over whole. Okay, so we can look at the mole values, part over whole, or we can look at the pressure values, part over whole. So in other words, it's like doing a percentage, but then you don't have to multiply by 100. Okay, so it's part over whole, just like a percentage. All right, So then let's take a look at the first example here. A volume, so we have volume, okay, we have 2 liters of helium, we have temperature, 46 degrees Celsius, and we have atmospheres, okay? So then we're having helium, and that's being added to 4.5 liters of nitrogen gas at STP. It wants us to find the total pressure and the partial pressure of each gas at STP after the helium is added. All right, so in other words, we have a container, and inside this container is the nitrogen. All right, then what we are adding is the helium into that container. So the first thing that we need to do is we need to find the partial pressure of each gas first. Once we find the partial pressure of each gas, then we can find the total, because remember, the total is each of the gases added up together. All right, so let's take a look at the helium first. All right, so let's go back, look at the problem. Helium, 2 liters, right? It's in a 2 liters of helium, 46 degrees Celsius, 1.2 atm. Okay, so then for the helium, with volume, temperature, and pressure given, what equation do you think we can use? Well, we can use PV equals nRT. But then if we use PV equals nRT, then what variable is missing? The moles, right? So then if we have PV equals nRT, we have pressure, so let's plug in the pressure. Pressure is 1.2. Volume is 2 liters. We don't know what N is. R is the gas constant, 0.00821. And temperature in Kelvin, so add 273 to 46, 319 Kelvin. Okay, so then if you finish solving that equation for N, we're going to find the moles of the helium that we are starting out with, and then I get 0.0916, that's a 6 moles of helium. Okay, but we're not done yet. We should find the pressure of helium because we need to find the partial pressure of each gas. So now that we know how many moles of helium we have, now we're going to use PV equals nRT, and this will give us the helium pressure, PV nRT. Now we're going to plug in the values for the nitrogen container. The reason why we're going to plug in the values for the nitrogen container is because the helium is being added, right, to the nitrogen vessel. So then the pressure is going to be different, right, when it is in this container, because this container has a different size and the temperature is also different. Okay, so then let's see. So then we're solving for pressure. So we don't know what the P is. Oops, go back. Okay, the volume is, it says right here, volume is 4.5 liters. All right, so pressure times 4.5 liters. We know the moles, we just solved for the moles, 0.0916. R is the gas constant, 0.0821. Temperature in Kelvin, well, it says that it's at standard temperature and pressure. Okay, the nitrogen container is at standard temperature and pressure, so then standard temperature is 273 Kelvin. Oops, 273. Eek. Oh, 273. All right, so solve for P. All right, so then if you solve for P, and this is for helium, I got, and I just rounded this to 2 sig figs, 0.46 atm. Okay, and this is for helium. All right, so that's for helium. So we know the helium pressure, we just solved for it. Helium pressure, 0.46 atm. Now let's look at the nitrogen pressure. Well, the nitrogen pressure is at STP, right? Because that's what the vessel, the nitrogen's in the vessel, so that's at STP. So what's standard pressure? Well then, standard pressure is 1 atm. So therefore, the pressure of nitrogen is 1 atm. ATM. Okay, so we have the pressure of nitrogen, we have the pressure of helium. Now we just need to find the total pressure. So remember, the total pressure is where you have each individual gas, those pressures added up together. So therefore, total pressure, PT, equals 1. Let's write 1. Trying to write 1 here. Hold on. Okay, 1 plus the 0.46. Therefore, that's 1.46 atm is the total pressure. Okay, there you go. So let's recap. Pressure of the helium was 0.46. Pressure of the nitrogen was 1 atm. We add both of those up together to get the total pressure of 1.46. All right, let's take a look at letter B. Calculate the number of moles of nitrogen present in the previous example. All right, so now we want to solve for moles of nitrogen. Well, the good thing for us, the nitrogen stuff is at STP, standard temperature and pressure. Therefore, we can just use the 22.4 liter conversion. So let's go ahead and do that. Because we know that the container it's in is 4.5 liters. Therefore, we put the 22.4 liters on the bottom, so those will cancel, and then the 1 mole goes on top. Okay, go ahead and divide those. If you do it correctly, you should get 0.2 moles of nitrogen. Okay? All right, then let's take a look at part C. Now we're getting into the mole fractions. So now they want us to use the mole fractions, or find the mole fractions of nitrogen and helium using 2 different pieces of data. The first method, they want us to use the mole data. Okay, then the second method, they want us to use the pressure data. All right, so let's do method number 1 first, using mole data. All right, so then let's find, so this is how you write the chi symbol for mole fraction. So the mole fraction for nitrogen, remember, doing a mole fraction is like doing a percentage, but we don't have to multiply by 100, so it's part over whole. So if we're doing the mole fraction of nitrogen, then we want the moles of nitrogen to go on top. Well, here are the moles of nitrogen. We just solved for the moles of nitrogen. Okay, it's 0.2, so then that will go on top, so 0.2 moles. Okay, remember, any percentage or percentage-like problems, part over whole. So that's the part. Now we need to find the whole. So the whole is the nitrogen, okay, the 0.2, plus the moles of helium. So if you remember, we solved for the moles of helium up here. Let me circle it for you. Right here, right? All right, so then we're going to add those 2 together. All right, so you're going to add 0.2 plus the 0.0916. Okay, so you end up having approximately 0.2 over 0.292. Okay, and then you should get 0.685. All right, so that's the mole fraction for the nitrogen. Now we're going to do the mole fraction of the helium. So once again, part over whole. So the helium goes on top this time, 0.0. You can round the 916 to 0.092 if you like. And then the whole stays the same, 0.292. Okay, then you get 0.315. All right, so those are the mole fractions for nitrogen and helium using mole data. Now what we're going to do is we're going to solve using the pressure data, okay, the mole fractions using, so this is a different method. So let's do this one in a different color. So let's do this one in blue pen. All right, so then the mole fraction of nitrogen, so part over whole. So if you look at the previous problem, what was the pressure of nitrogen? Well, if you remember, the pressure of nitrogen was 1 atm. Okay, so 1 goes on top over the total pressure. We solved for the total pressure. So the total pressure was the 1.46 that we already added up together. Okay, and that is 0.685. Do the mole fraction of helium using pressure data. So if you look above, the pressure of the helium was 0.46 over the total 1.46, and that equals 0.315. All right, so the main thing that this is demonstrating and showing, it's showing you that no matter what data you use, it's going to give you the same mole fraction. Okay, notice those nitrogens. We found the mole fraction using mole data and got 0.685. We solved for the mole fraction of nitrogen using pressure data and we got the same answer. Okay, same thing for the helium. All right, we got the same answers, right? 0.315, 0.315. All right, so that's why so if you look at the very top of the page, that mole fraction equation right here, it's showing that no matter what data is provided, whether it's mole data or pressure data, that those are equivalent, okay? They'll give you the same mole fraction, all right? So once again, depending on what information is given in the problem, that's how you will determine how you're going to solve for mole fraction, okay? So that is everything that I want to cover for today, and I will see you later. Good night. Bye.